This question is, this is the quiz that was taken March 11th in astronomy, studying nuclear physics. The following particles are used to describe the structure of an atom. Underline the fundamental particles in the above list. So a neutron and a proton are subatomic particles, but they are not fundamental. They are made up of quarks, which are the fundamental particles. Electrons are also fundamental. Okay, they're a class of particle called a lepton. Leptons, like electrons, fundamental. Quarks are the fundamental particle that make up these particles, which are important. They are subatomic, but they're not. They can be further divided. So the pictures like this one that we have been studying this week kind of prove like, oh yeah, proton is 3 of these things. Those are the fundamental ones, right? The quarks. The next question is about beta minus decay. So yesterday we saw some examples with beta plus decay. So you have to kind of just rely on your notes or think a little bit carefully here to not just mimic exactly what we did yesterday, because different types of beta decay, right? So this is beta minus decay. So the following equation represents the decay of a nucleus of cobalt-60 to form nucleus Q by beta minus emission. Complete figure 7.1. They give you the reaction there, and the key idea is that the proton number is going to be conserved and the nucleon number is conserved, and we know that a beta minus particle has a charge of, -1. Okay, so it's like an electron. This is the transmutation where a neutron inside of the nucleus becomes a proton. And so if a neutral thing becomes positive, it's like, well, how did it do that? It kicked out the negative charge. So this negative electron comes from the nucleus. It's a beta particle, has a charge of -1. So if one of these nucleons, one of these 60, that was a neutron, became a proton, then we don't have 27 anymore. We go 1 up on the periodic table. So this is going to be something with 28 protons. So if you got 28 down here, well done. Something with 28 protons is nickel. Okay, so this would be nickel. And then we're still going to have 60 nucleons, right? So we just change a neutron to a proton, but the total number of them is unchanged. It's just that the atomic number goes up. So 60, 28 should have been what you got for this one. And then this particle X over here, because this is a regular bit of matter, electrons, regular matter, right? Then this is going to be our antiparticle. So we get an anti. If you want to be really specific, it's called an electron neutrino, but you could have just said anti-neutrino to earn this mark there. More specifically, they're just like different flavors of quark, up, down, top, bottom, strange, charm, different flavors of neutrino, tau neutrinos, muon neutrinos, but these here are electron neutrinos. So it's an anti-electron neutrino. All right, 1, 2, 3 marks for this part of it. Here's where you just want to be very honest with how many of these marks were you able to earn on your own. 0 out of 3, 1 out of 3, 2 out of 3. You give yourself a half a mark. If you did corrections just now, if you're like, I put 27, or I put 20, I went the other way, I thought beta plus and I went down or something. Make the correction and give yourself, partial credit, half the marks or something like that. Okay. The rest of the quiz is there will be some, like I said, that you kind of want to try on your own, but there'll be a lot of freebies in there to help, boost your grade here. So even if you got 0 out of 3 on this, just kind of give yourself feedback and say, why did I get 0 out of 3? It's because I forgot that a quark was the fundamental thing, because the Greek word atomos means indivisible. So we shouldn't be able to divide it, but we can divide atoms. All right, the next one that we're going to do is maybe this one. Nope. This one? Nope. Nope. This one. All right. This one says a sample of rate. So this is part 2. So you can just kind of like call this. That first question was 7, or you might have called it question number 1 because it's the first one that we did. Just kind of keep track of it. This is the second part, and it's question 7, and it's A, B, C, D. It says a sample of radioactive substance may decay by emission of either alpha, beta, or gamma radiation. State the type of radiation, one in each case, that. So there's only be one. The answer is either going to be alpha, beta, or gamma, okay, for each of these. We want one, the first one, A, the one that consists of leptons. I'm not going to give you too much time to think through this because we're recording right now, and people on YouTube, they want to know the answer here. And I'm just going to wait for you guys to answer it. Okay, so I feel like I've delayed long enough. Say, okay, leptons. Just mentioned a moment ago that the electrons were leptons, and so which one of those up there is electrons? That's our beta radiation, right? So beta radiation, because it's electrons, those consist of leptons. Alpha radiation, remember an alpha particle is a helium nucleus, right? So it's made of quarks. Hey, there we go. It's like protons and neutrons. They made of quarks. But the electrons are not, right? So it's only one in each case. The only one of those that contains quarks is the alpha particle, alpha radiation. Cannot be deflected by an electric field. So an electric field is going to affect charged things like beta minus particles or positrons, right? There's two types of beta radiation. So it'd be like beta plus or beta minus. Both would be affected by an electric field. So beta radiation would be this alpha particle is positively charged because it's got two protons. There's not two electrons. This is not a helium atom, okay, with two electrons. It's just a helium nucleus. So it has a charge of +2. And so both of those things would be deflected by an electric field. Here is on Monday, I think I gave you some time to kind of click through some of the slides that were uploaded into Focus. And we spent a lot of time with like this slide, just kind of appreciating quark nature. But if you made it all the way down here, okay, you can see that a beta particle, because this is the electric field would be in here. So here's a radioactive source that's emitting all three of these types of radiation. As it passes through this electric field between these magnets, the negative beam, these beta particles that are, electrons, they're going to get pulled towards the positive plate, so they deflect this way. The alpha particle is positively charged, so it gets pulled towards the negative plate, but it doesn't deflect as much. You see how this is a steeper angle than that one? That's because the alpha particle is more massive. This is just an electron, so it's actually, it would be way worse. Like this thing would just go like straight up. This thing would barely be deflected down. But the gamma rays, they're not deflected because they're not charged. So gamma radiation is the answer to that one, right? They just go straight through. The electric field does not affect light. So we got beta, alpha, cannot be deflected by an electric field, gamma. And then the only one that can have a continuous range of energies is beta radiation, okay? Discrete energy values is like photons, okay? So photons of light, this is sort of Einstein's contribution to quantum mechanics. He wrote a photon paper and said, we should think about light as not just waves, but also as like packets of discrete sort of energy, quantized light. So we call those photons now. And alpha particles also only exist as sort of discrete values of energy. So only the beta particles could have a continuous range of energies. All right, the third one here is really the tough one, part 3. Looks right. So we're going to do question number 12. This is more along the lines of what we were doing with fusion and fission. So this is another fission reaction. It's in fact, I think the same one that we've been sort of looking at. It's just a different question sort of belonging to it. So this one is just going to be reinforcement. We're going to work through this one together, or you might say, I'll just kind of pay attention here and then get it all down sort of at the end here. But remember, my working is fleeting because I'm always erasing it, so you might want to keep up with it here. The first one just says, show that the energy equivalent to a mass of 1 unified atomic mass unit is 934 mega electron volts. We've done this exact calculation before. So if you go back a few weeks ago, we did this, one on a quiz or as a review for the quiz. Here we just need to remember that a unified atomic mass unit in kilograms is 1.66 by 10 to the negative 27 kilograms. And so we're using Einstein's famous E equals mc squared, where 1 U is this many kilograms, and then we're going to multiply by c squared is 9 by 10 to the 16. So the speed of light is 3 by 10 to the 8 meters per second. So if we square it, 3 squared is 9, 10 to the 8 squared is 10 to the 16. So we're just sort of multiplying these two numbers to get joules of energy. And then you may recall that there are 1.6 by 10 to the negative 19 joules per electron volt. And there are 10 to the 6 electron volts per mega electron volt. So we can kind of collapse this conversion into just one step. We could say, well, if there's this many joules per electron volt and this many electron volts per mega electron volt, can't we just say how many joules are in a mega electron volt and sort of cancel out these electron volts? And we can. We would just multiply these two in the denominator to give us that whatever we get for joules, which is the product of these two numbers, right? MC squared, so plug in that for M. 1.66 by 10 to the negative 27. Plug in that for M, this number. And then you'll have joules of energy, right? Because kilogram, the units here are meters squared per second squared. Those are joules of energy. Then we can take those joules of energy and just divide it by 1.6 by 10 to the negative 13 joules per mega electron volt, okay? And that's just saying if there's 10 to the negative 19 in an electron volt, but mega is 1,000,000, then we just need to sort of make this 1,000,000 times bigger, you know, so we add sort of 6 to that and it becomes negative 13. So that's just this conversion here. 1.66 by 10 to the negative 27 times 9 times 10 to the 16 gives us in joules 1.494 by 10 to the negative 10, which we then divide by 1.6 times 10 to the negative 13. And we get an answer of 933.75 mega electron volts, which is indeed about 934, what we were supposed to show. So 2 marks for that. And really, we were doing this calculation earlier today, and we're kind of saying like, well, this was kind of a nice way to just give you a conversion also from this unit, unified atomic mass units, into mega electron volts, because that's what all the binding energy sort of is reported in over here. So because this right here is blank, we can anticipate they're going to ask us to calculate this. And that indeed is the next, I don't know if it's the next one or the one after that. I think it's the next one. Yeah, it says use data from the table to calculate the binding energy per nucleon of a nucleus of uranium-235. So very clever students would be able to kind of look and see, well, they've already done this calculation for these two. So we could just sort of mirror whatever they did here if we were, you know, clever enough to figure it out if we didn't sort of know how to go about it. The binding energy per nucleon is what we calculated for iron when we looked at this graph, the binding energy per nucleon versus the nucleon number. And we said, like, as you climb up the periodic table, you get a peak at iron, which is number 56. It has a mass of about 56. And then things heavier than that fission back, right? Things lighter than it, you know, fusion towards. But iron has the highest value. So we're calculating sort of like this value on the y-axis. This is the binding energy per nucleon against the nucleon number, which is like this number at the top here. So remember how we do this. We have to figure out the difference between the mass of the actual atom, and if we were to separate all 235 nucleons apart from each other and added up their individual mass, it would be this. So there is a difference. There is a mass defect. The first thing you could do to prove to yourself that like you're on the right track with that is it should be that whatever number is in this column, subtract this number, and that's how they're getting this number, right? This column here is just the difference between these two. There is more mass in the separate nucleons than there is in the atom when they're all bound together because they're bound together. It costs energy to keep all those protons stuck together in the nucleus. And that energy sort of shows up as a difference in mass. Why? Because of this, E equals mc squared. So if there's a difference in mass, it's really like, oh, they're accounting for the energy that's locked up inside of the nucleus that could be unleashed, right? Like in a reaction like this. So 236.909 minus 235.044 is indeed 1.865. That's the mass defect. To get the binding energy per nucleon in mega electron volts now, we're going to multiply this by 934. Or actually, let's do it by 933.75, right? Because they've already told us what one unified atomic mass unit is in terms of this energy. So we can just use this now as a conversion. So I'm going to take 1.865 unified atomic mass units times 933.75 mega electron volts per unified atomic mass unit. So now I'm in mega electron volts, but this is for the entire nucleus, right? Because that's all of the mass defect. So the entire nucleus has this much binding energy. We want the energy per nucleon. So we have to divide it by the number of nucleons. There's 235 nucleons in this uranium. So we take this product and divide it by 235. So in your calculator, if you've got 933.75 still there from this calculation, we're going to multiply that by the mass defect, 1.865. And that gives us 1,741.44 mega electron volts in the entire nucleus. So per nucleon now, divide that by 235 nucleons in this uranium atom. And we find that the correct answer here is, so what should go in this, like the calculation is this number times this number divided by this number. What does that lead to? 7.4. And then the units are already up here, mega electron volts. So when this uranium fissions, do you see how the products, molybdenum and lanthanum, have more binding energy per nucleon than the uranium has? That means they're further up this, right? And it makes sense because they have less nucleon number. So we already know that uranium would be further down this graph. The reason why this reaction goes is because these things are more stable. So uranium would rather fission and become more stable products, or you could say the universe would rather have that happen because the universe tends towards low energy and stability. So 7.4 is the answer to that one. If you needed to get any of this working down in your journal, so just have a look on YouTube at the end of class. Here it says the nucleon number of an isotope of the element Rutherfordium is 267. State whether the binding energy per nucleon of this isotope will be greater than, equal to, or less than the binding energy per nucleon of uranium-235. So this, once again, is just a conceptual question that's sort of seeing whether or not you've got that graph in mind that we just had up there, right? So iron is at the peak, and uranium is 235. So remember, nucleon number, like iron is like 56 right here, 235 would be way out here. So that's uranium. Rutherfordium is even further down this, right? So Rutherfordium would be up here. So as we go from sort of right to left, all the way up to iron, which is at the peak here, we're finding that these things have more and more binding energy per nucleon. So compared to the uranium-235, the binding energy per nucleon of this isotope will be less than, right? It's going to be further down sort of this graph. So higher up on the x-axis because the number is bigger, but we know that the plot goes like this, right? It starts to decrease after iron and keeps going down. So if uranium can fission, Rutherfordium can fission even better. Okay, it's even more unstable. So the answer to that one is just less than, right? And it's really the graph of the binding energy per nucleon against nucleon number that helps you sort of solve that. This is a really important graph in terms of why does the universe have so much iron in it? You know, it sort of really helps us to anticipate which type of nuclear reactions will go. Now this one, the way I calculated this earlier was incorrect, or it's kind of incorrect, I should say. When I took a look at the mark scheme, it didn't agree with it. So I'll tell you, the way that I calculated it earlier was to sort of it wants the energy released in this, and I thought, oh, maybe there's some clever way to do it, the mass defect, but I wasn't really sort of, willing to rack my brain over it. So I just added up the mass of this, and I added in the neutron as a unified atomic mass unit. So I did the calculation the way that we had done before, like add up all the mass on this side. Here they give you the mass of the products. And I added in sort of the neutrons here just as a unified atomic mass unit. But then we're neglecting the electrons, right? They don't tell us anything about the electrons. So you really are required to kind of use this information or this information to calculate it. There's two ways to sort of go about the calculation. Remember, this was 7.4. And if we know the binding energy per nucleon, then we could multiply these by the number of nucleons and then take the difference. Like there should be more on this side than there was on this side because we're liberating energy. And then so we could then convert that into, well, I guess it already would be in mega electron volts because it wants the answer in mega electron volts. So I think the path to the solution is 8.443 times, so this is per nucleon. So we'd say, well, there's 95 nucleons in that one. So this would be like all of the energy that's sort of in the molybdenum. And then we've got the lanthanum, which is 139 times 8.189. And that would give us sort of like the total energy on this side minus the 7.4, and I guess this was 7.41 times 235. And so this should be the energy released because it's like, or maybe we have to switch that around and we have to subtract those away from that. Let's see which one's bigger. All right, so we got 8.443 times 95 plus 8.189 times 139. So that gives us 1940.356. And then 235 times 7.41. That's 1741.35. Is that right? 139 times. You get 1940.356 minus 1741.35. And so the energy that's liberated in this reaction is, again, the difference between these. And so it's sort of the difference between the nucleon number times the binding energy per nucleon, taken away from the binding energy per nucleon, because these are more stable, right? They got more binding energy per nucleon. So we're sort of seeing, they'd be higher up sort of on this plot. Take away the total sort of binding energy of this nucleus, right? So by multiplying the binding energy per nucleon times the nucleon number, you're getting the total sort of binding energy in that nucleon. So when we fission that, we're releasing it, but then we have to account for the fact that, well, these things still have energy locked up in them, so it is indeed the difference between those two. And so you should get 199 for that. So part C of this is, there's the working for it. So like 1940 minus 1741 gives you 199 mega electron volts. Okay, that's the energy that's released. And that is for each reaction. Okay, so in a single reaction, we can release, sort of this much energy. The last question is, the nuclei in this many moles of uranium-235 all undergo this reaction in a time of 25 milliseconds. Calculate the average power release during the time of 25 milliseconds. All right, so let me show you sort of the physics. And it's like some chemistry too. So start with what you're given. Mole is a word like dozen. Dozen doesn't matter what you got, right? You got a dozen eggs, you got a dozen donuts, you got 12. Mole is like that. Doesn't matter what you have. You have a mole of atoms, you have a mole of moles, you have a mole of whatever. So it's just a number, and that number is 6.02 times 10 to the 23. That's why October 23rd is Mole Day. Okay, this is the things in a mole. So we've got 1.2 by 10 to the negative 7 moles of uranium-235 times this many, atoms. So we could say this is atoms of uranium in a mole of uranium. And this is how many moles of uranium I've got. So the first step is to just say, if I'm releasing this much energy per reaction, each atom of uranium, right, releases this much energy as it fissions. Well, I've got a whole bunch of uranium atoms here, right? I've got this many moles. So that's going to give me like the total number of uranium atoms. Then I'm going to multiply it by this much energy. So multiply that by 199 mega electron volts per atom of uranium. And then that's going to be energy, but not in the units we want. So power is measured in watts. So we need joules per second. So we need to convert back from mega electron volts to joules. You may recall from a moment ago, there was 1.6 by 10 to the negative 13 joules per mega electron volt. And then we'll be in, so we cancel out moles of uranium, we cancel out atoms of uranium, we cancel out mega electron volts, joules per second. So 25 milli is 10 to the negative 3. So that's how many seconds there are. In other words, power is the rate at which energy is converted. We're converting a huge amount of nuclear energy into who knows what, kinetic energy of the product, the photon energy of the gamma radiation that's released, heat, sound. This is like a nuclear bomb. Okay, so we're calculating the power of a. You could say, well, maybe it's controlled. Maybe it's happening in a nuclear reactor controlled, or maybe it's being released, in 25 milliseconds. That's a short amount of time, right? So the last step here is to just multiply everything in the numerator and then divide by, I guess that's really the only value besides, like these are all just ones, 199 per one atom, per one mole. So we're going to take our calculator. I've still got this number in my calculator, 199. So I'm going to start there. Times 6.02 times 10 to the 23 times 1.2 times 10 to the negative 7 times 1.6 times 10 to the negative 13 divided by 0.0025, right? 2.5 by 10 to the negative 3. And I get 920076.380.2 watts. That's a lot of watts. 920 million watts. So we could say 920 megawatts. I feel like we might have missed an order of 10 there. Let's just double check that calculation. I got it. All right, let me check this again. 1.2 by 10 to the negative 7 times 6.02 by 10 to the 23 times 199 times 1.6 times 10 to the negative 13 divided by 0.0025. 2, 3, 4. Yeah, if I get like 900, well, that time I got like 947. But I don't know what I did. I just had I guess a small change here when you multiply by 10 to the 23 is a big change. Somewhere around there, like 900 megawatts, something like that. All right, for everybody that's following along at home, anytime you're practicing through one of these papers, you can just change in the address bar up here where it says QP question paper, make it MS for mark scheme, and then all the answers will show up. For some reason, I feel like, did we go wrong somewhere here? All right, let's check this now. So this was question 12. 9.2 by 10 to the 7. Is that right? 10 to the 8. Or did we get 10 to the 8? 1, 2, 3, 4. We got 10 to the 8. The mystery for another day. All right. Go ahead and let me know how many of those first 3 marks you got. The rest of the quiz, I think it was like 18 total marks. So you're guaranteed, as long as you sort of followed along with that, you're guaranteed, I guess, 15 out of 18. But then let me know how well you did on the other 3. If you want to turn in your journal today, you can. If you prefer to wait until the Monday that we come back after spring break, I suppose you could turn it in then. I'm not going to be here tomorrow, so hang on to it until Monday if you don't plan on turning in your journal today. All right, you still have more than 30 minutes left in class. Please focus on any makeup work that you might need to do to help bring up your grade. You got the rest of the class to use as you see fit, and you got tomorrow to do the same thing, to work on makeup work. So use your time wisely.